introduction to the analysis workflow. The first thing what you have to be aware of is the modeling task at hand. And here the question is, how should you approach this modeling task? And this is only one guideline. The first question you should pose to yourself is actually, what is the question the simulation should answer? And this will give you the answer to the required modeling abstractions. So what are the governing equations? Are they linear or non-linear, for example? What kind of analysis type do you need? Is a statics analysis sufficient, or do you have a time-dependent problem? What boundary conditions do you have to apply? Because the boundary conditions are actually the things that relate your model to the physical model behind. So the actual engineering application, for example, at some point you have to truncate your model, and that's where you have to assume some boundary conditions. You also typically need to think about what geometrical features are necessary. Is it, for example, necessary to consider surface roughness, or can I assume a surface as ideally flat, or are there symmetries in the domain that you can use to decrease your simulation effort? And then, of course, number 3 is, what simulation tools do you use for your analysis? Okay, our example problem now is heat conduction in 2D, not really in 2D. We will see this later when we look at the solution, but let's start like this. We can consider a rectangular domain. One dimension A is 1 meter, one dimension B is 0.5 meters. And then we have given temperatures on the left-hand side. So this could be inside of a room with 25 degrees Celsius. And on the right-hand side, we have minus 10 degrees Celsius. Then we also assume we have perfect isolation of the upper and lower boundary of the domain. And we have an isotropic heat conduction coefficient K equal to 1 watt per square meter per Kelvin. And the question the simulation should answer in this simple case is, what is the transmitted heat flux through this wall? Okay, so much for the simulation problem. Our steps in the simulation workflow will be meshing with Trelis, the definition of our simulation input with an XML editor. We use Oxygen XML for that. Finally, the simulation. We'll use our finite element code CFS, developed at the Institute of Mechanics and Mechatronics. And finally, we'll do post-processing and result presentations. In this case, we'll use ParaView, which is an open source data visualization software. Okay, we probably need to do is get a little bit familiar with the Linux environment here. First, we'll open a terminal window here, and here you can enter commands. For example, to know where you are, you enter the command pwd. It prints the working directory. So this is home user, as you can see from the output. The next thing is we want to unzip our template files, which were given, which you can already find on Tuvel. I've mounted them in a shared folder. With ls, I can list containers of the folders. So under media SF tutorials, I've mounted a shared folder where you see there are a few zip files, and we'll deal with analysis workflow.zip. So this is what we want to unzip. So we type unzip, and now the path of analysis workflow.zip, and it will unzip this directory in our working directory. Just note, in Linux, you can copy and paste by simply marking a text and then pressing the middle mouse button. It pastes it in the location you click the mouse button on. Another helpful feature in the Linux terminal is tab completion. So whenever you press tab, the terminal tries to complete the command you're typing. So for example, if I start typing un for unzip and I press tab twice, I get all the commands that are available starting with un. So by unzip, typing unz and pressing tab again, I get the unzip command. Another important feature of most of Linux commands is the help flag. So unzip -h will give me a help output directly on the terminal, where it usually tells you all the options that the command has. So whenever you're unsure what the command does, try the -h option or type man unzip, which gives you the man page of the command in question with a more detailed description. Okay, so much about Linux. I think these were the most important tricks that are not immediately obvious. Use tab completion. The middle mouse button can be used to paste, and copying is done by simply marking some text. Okay.
I have a question.
Yes.
Where does it unzip the files? In the
working directory.
Okay, working. Okay, thanks.
So I'll list them now in my working directory. You can see analysis workflow has appeared here. So we can change to this analysis workflow directory. Again, tab completion makes typing much faster. So we change here, print working directory to verify where we are, and ls to list the container contents of this directory. Okay. First step we have to do is to mesh our geometry with Trelis. So to start Trelis, we simply type Trelis in the command line, and another Linux hint, put the ampersand behind the command to get your terminal free again. So to send the command into the background. Okay, so Trelis opened here, can maximize the window. How does the Trelis window look like? We have a viewport here in the middle. We have a command line window here. And most importantly, on the right-hand side, we have the command panel, which we will use to create our geometry. And last but not least, we have the model tree here, which where we will see the results of our command in the model layout. So the first thing we want to do is we want to create geometry. This is the geometry mode here. So we choose this one. We want to create geometry. So this is selecting the operation, and we want to create a surface. So our 2D model, and we click the surface button. We see we have a lot of options. In our case, a rectangle will be useful. The width was 1 meter. The height was 0.5 meters. And the plane should be in the Z plane. This is the convention for 2D simulations in CFS++, that the geometry is defined in XY coordinates. So we click apply, and we have our structure here. You can see sheet bodies, body 1, volume 1 appeared here. It's composed of surface 1, which has 4 bounding curves, and the bounding curves are bounded by vertex 1 and 2 for the curve 1. So you can see here in the model browser, you have all the hierarchical structure of the model. The second step is meshing. So we, in the command panel, switch to the mesh mode. And here again, we want to mesh surfaces. And the only thing we want to specify here is define size and intervals. And we can use the automatic sizing option and simply click mesh here in this case. What we do have to do is to select the surfaces we want to mesh. Otherwise, clicking mesh doesn't have any effect. So click mesh again, and here we have our beautiful, very simple structured mesh of our wall domain. The last thing we have to do in Trelis is to define surfaces or regions where we later will apply our simulation domain and boundary conditions. So the first thing we want to define is regions for specifying boundary conditions. We need boundary conditions on the left and the right hand side, and this is done by so-called node set. So this is this button here. We want to again create a node set. We want to give it a descriptive name that we will later use in CFS. So as it's a line region, I call it line underscore left for the left one. And we actually want to select curve, and we can simply click on the curve on the left hand side and hit apply to create our boundary. And you will see the node set appeared here in the model tree. When you select it, you see what the name left actually created. So let's do this again for a new node set. Delete the ID, call it L right. And this is not ID 2, but let's see, ID 4, click apply, and we have on the right hand side an equivalent node set. The last thing we need is the so-called volume region. In this case, is a 2D simulation. This will be a 2D surface, and for this we have to define so-called blocks in Trelis. So again, choose the block, choose the action, which is new. We want to create a block. The block ID is S wall. It says since it's the surface of the wall, we want to select the surface, select the ID, click apply, and we have in the model tree a block that is called S wall. So finally, we have to export this mesh to a format that CFS++ can read, and to export it, you can either use the export button here or choose file export. The correct export format for us now is the ANSYS CDB format. This we can read with CFS++, and we'll call the file wall.cdb. It's already available in the templates you have seen, so we'll just overwrite it. So let's click save. Yes, we want to overwrite it, and we want to export all. Click finish, and it has been exported. You can see here in the command window, the export has been finished. So basically, we're done in Trelis. If you want to, you can use, you can save this also as a Trelis file. Then you can later continue with modifying the model. Also, the Trelis file of this simulation is already present in the examples, so you can have a look at it, or for example, change meshing parameters later. Let's do this for CFS++. We use an XML input format. I've already provided 2 XML files for you. The first one is simulation input.xml, which is a simulation input. And the second file is mat.xml, which is the material definition. And we'll simply open both with our XML editor, which is called Oxygen. And if you directly specify the file name as an argument, it will directly open this file for you. So let's wait until Oxygen starts up. So it takes a while to load on the virtual machine. There's the new version available. Okay, again, maximize the window. And here you can see the XML file, which is defined as an input. You can see that there are different file formats. So let's go through the section of the input files. You have the documentation section. You have the file format section here. You have the domain section, which specifies the material assignment. And we have the so-called sequence step section, where we can define a set of sequence steps. So this is index 1, and it only contains one. And here the important sections are the analysis type and the PDE list, which can in general contain many PDEs and couplings. And in our case, we only have the heat conduction PDE defined. Okay, so from top to bottom, file formats, this is the first important section for you. It specifies the input file, and we have a CDB file. The file name is given as wall CDB. You can also see that Oxygen actually reads the so-called XML scheme and tells you which commands are valid. So you can see here, I've opened, I put the cursor into one tag, started typing by putting a space, and it shows me which other options are available for the CDB tag. If I put my cursor here, I can also see which other input file formats are supported. So I can navigate here. Gmesh, it also gives you a little bit of documentation for some commands. So Gmesh command reads files generated by the Gmesh software. Okay, we don't need to add a Gmesh input now. The other important section here is the output section. HDF5 is usually always present in all our template files, because this is our default output format. It will be written in the results HDF5 directory. And we could also define text-based outputs, which will simply write ASCII files. And finally, we have the material data file referencing mat.xml. Let's directly look at this file by opening it up. So we'll open a new file here, mat.xml, and we see how the material file looks like. So in the material file, we specify a material table, not all these materials are used, only the ones that are actually assigned to some regions are used. So here we have, again, XML structure. We have a material named concrete, and we define properties for heat conduction. The property density is linear and real value, that has the value of 2,400. So you can now guess that we are in SI units, and this is the density for concrete in kilograms per cubic meter. So for the other units, we also have to stick to the SI unit system, since CFS, like many finite element codes, is by default unitless. So we define the heat capacity, again, a linear and real valued property, in joule per kilogram per Kelvin. And again, we have to define the heat conductivity, and we've seen in the assignment that we use a value of 1.0 here, again in SI units. Okay, so let's switch back to our simulation XML and see where this material is actually assigned to the region. This is done in the domain section, where we have a region list and only one region present. The name of the region is S-wall. So you recognize again the name we have used for the block in Trelis, and we assign the material concrete, which is the name of the material we have in our material database. And finally, we can go out to our sequence step. We define a static analysis. We can also see with which other analysis types we would have. One important part is sometimes the XML tags have a specific order. So if we put the cursor before analysis, we see a few other types appearing if we start to type. If we put it afterwards, there's nothing possible, since you can't do two analysis types at the same time, and static is already present in the XML scheme. So what we need to do in our PDE definition, the first thing each PDE has is a region list again. So we have to define which regions should be incorporated in the analysis in this case. In this case, we only have one region defined, so we want to incorporate this. So again, we put the name as wall here. And the other important section is boundary conditions and loads. And here we can specify the temperature boundary condition. So we again have to reference the name where it should be applied and the value where the inhomogeneous Dirichlet condition should be set. So we specify plus 25 for the left side and minus 10 for the right side. Let's see what other boundary conditions we could put. We could put a heat flux, we could put heat sources, we could put heat source densities, heat transport, periodic boundary condition, and a few other things. The final important section for a PDE is the store result section. And here we have two types of results. We have the node results, which with the type heat temperature, which should be output on all regions, and the element result heat flux density, which also should be output at all regions. Okay, so this was all. The only thing we have to do is save our input file and head over to our terminal, where we can run CFS++. And this is done. What we have to do is save our input file and head over to our terminal, where we can run CFS++. And this is done by the CFS command. Again, let's look what the help options tells us. We can see the command usage is CFS, some parameters, and name of the simulation run, which is required. The optional parameters I typically like to use is the -p option to directly specify the parameter file, so the simulation input. So let's do this, CFS -p simulation input.xml, and the job should be called job. If we run this, CFS runs in 1.6 seconds for this very tiny analysis, and it creates a result HDF5 file called job.cfs. Okay, so this was how you run CFS. Again, I'll process simulation results with from CFS. We use ParaView. So we can start it in the virtual machine by simply typing ParaView and again an ampersand at the end, so the terminal gets free. ParaView starts up, the start screen we can disable. This is how the ParaView window looks like. You have first of all a viewport again where you will see the geometry, and then on the left hand side you have the pipeline browser and some toolbars with frequently used tools. So the first thing we want to do is to open result file. So we click on file open and choose our CFS file, which is located in the results HDF5 directory and called job CFS, because we have run CFS with the parameter job. Okay, so here it is. You can already see here in the pipeline, in the properties window, which regions you want to import. Let's import all of them and click apply, and then it will appear in the viewport. You can see we have three regions here. They're given in different colors. You can faintly see the white color on the left-hand side, which is L left, and the red color on the right-hand side, which is L right, and the green color for S wall. So the colors are always given in the order of the regions here. We can untick the surface regions because we have not saved any results there, so they don't contain any result data. Click apply there and reload. So now our wall region is white. We can also change the representation of this job.cfs file. Here, the pipeline browser, it is marked. If we change from the surface representation to, for example, surface with edges, we also see lines for the elements that we can recognize our mesh again. Okay, so this is the display. What we're currently displaying is shown here. We're displaying VTK block colors. What we want to display is actually our result, so heat temperature. You can see here by the symbol, this dot symbol means we have point results, so at the nodes. So let's activate heat temperature, and we can see here now in colors the temperature field displayed in the legend. You can move it around. Let's put it here on top. We are going from -10 at the blue color to +25 at the red color. So you can modify the color map. If you don't see the color map window, you get it here by the element color, edit color map button in the toolbar. You can here choose a few properties of the color map. For example, we only want to have, say, 10 discrete colors. Click enter, hit enter, and you get the colors now it's discrete colors. What we can also do is we can actually adapt the legends of this color map such that 0 is exactly where we have the change from red to green color. So you will have to extend the range here. So let's say we want to go from -25 to +25, hit rescale, and you see the 0 goes exactly where we have the red color. So for our application example, this is where the danger in the wall starts, where we have sub-zero temperatures, because here the humidity in the wall could freeze and lead to damage, for example. Okay, so this was displaying the temperature field. The last thing I want to show you now is how to show the vector field, and for this we apply a so-called glyph filter in the pipeline. So our visualization is always processed from top to bottom. We will add a new filter here now, which is called glyph. This requires orientation area input, and here we use the heat flux density. So let's click apply again, and we see that the vector field is appearing. Again, the vector field is colored by solid color, and you can use a few useful parameters. For example, we can determine at which points we want to plot the vectors for small data sets. Usually it's useful to plot at all points. So click apply again, and we have all our vectors. We can also scale them a little bit smaller. Let's say we want to have them half the size. Click apply. We have a bit smaller vectors. And let's say we want to color them by the heat flux density to know the value. Again, you see another legend appears here, and you can see the values are actually going from 35 to 35. So we have a constant field of the heat flux density as it was expected. And you can verify the value by doing the analytic computation of this very simple problem.